We have here a graph of the acceleration in meters per second of a cart rolling down an incline versus the slope of the incline. Recall that we obtained this information by allowing the cart to start from rest and coast down an incline, measuring the time required to coast a given distance from rest. From that we were able to infer the acceleration, so that for each incline, for example an incline of 0.04, we might get an acceleration here. If this is 1 meter per second, maybe that's 0.4 meters per second, and so forth. So we have here represented just 3 points. In a good experiment we'd want to have at least 6 or 8 points to establish a straight line model, because theoretically we expect the graph to be nearly linear for a small value of m being the ramp slope. So for small value of the ramp slope we expect a nearly linear straight line, a nearly linear curve fitting the data points. The ramp slope less than 0.1 or less than about 0.15 would be considered small for our purposes here. The graph slope might turn out to be a run of 0.1 meter, a rise of 0.8 meter per second, giving us a slope of 8 meters per second. The accepted value of the acceleration of gravity is 9.8 meters per second, and the graph slope should be identical to the acceleration of gravity. So what we're doing in this experiment is we are measuring the acceleration of gravity. Now the results obtained by various groups in the class varied. Some results were fairly close to the accepted value and some results were way off. And there are a variety of reasons for that we're going to look at. Again, the graph slope ought to equal the acceleration of gravity, dividing the rise in meters per second by the run, which is a unitless quantity. We will get units of acceleration. And that doesn't prove that this is the acceleration of gravity, but later we'll see why we expect this to be the acceleration of gravity. Slopes observed in the class range from a low of 220 to a high of 2,000 centimeters per second. The accepted value 9.8 meters per second. 9.8 meters is the same as 980 centimeters, so 980 centimeters per second. We see some results, 830, 880, 1,000, 1,200, even 1,300, reasonably close to 980, with an experimental error of maybe 20, 25, or a little more percent. But some of these results are way off. And we raise the question of how could we be this far off? Well, it turns out that there are going to be two reasons. One reason is we might have made an error in our calculations. And there's not much we can do about that except to fix our calculations. Of course, if we have good data, that's easy enough to do. The other thing that comes up, though, is that in some cases you have unavoidable experimental errors. And in some cases there are avoidable experimental errors, and we'll discuss what some of those might be.